Hello, everybody. Good morning. This talk explores how network infrastructure defines platform potential. Traditional apps scale differently than AI platforms, which require ultra low latency and massive scalability. The network can either empower or cripple modern systems. I will take a deep dive how a network is very crucial in modern AI era. Your network is, we all say, the weakest link. The strength of a chain is its weakest link. So it's applicable to network as well. The network is either your platform superpower or actually let's say network here, all the devices which does the packet processing capabilities, how the packet is forwarded from any user all the way to the server and the return packet from the server to user. You experience the internet, its fastness, it's how you feel as a user. That's the one decides any product in the market, be it is its simple application or be it's a very e-commerce platform or it an app. So underlying there is so much networking concepts, then so much networking is involved. So today we're looking to how some of the case studies, how networking plays a key role. We will cover architectural evolution, networking failure modes, principles of fault tolerance, network observability strategies, and real world case studies, and around those concepts. We have moved from traditional three-tier architectures. There were core, distribution, access to spine leaf models where two spines are connected through a leaf switch optimized for particularly these optimized for east-west traffic because of the tremendous AI and tremendous activity in the data centers. The traffic not only is from the north to south, meaning the user to server, but also there is a lot of computation. There are a lot of calculations involved within the data center before the response is sent to the user. This has become even more prevalent in AI data centers, where the distribution nodes have grown tremendously from 2 to 4 a simple web scale traffic to 128 to 256 nodes in the case of AI network. Software defined networking, of course, because of the lot of nodes involved in the data centers, software defined networking, which enables the programmability. Basically, you are able to program a lot of devices at once so that the DevOps, those particularly the duties revolving around the DevOps will become pre- much more easy and predictable, less error prone, and etc. Of course, AI scale requires specialized ASICs and ultra low latency fabrics. There is so much of hardware. There is so much development in the hardware also is happening, particularly ASICs are built with ultra high speeds and ultra low latency. The whole data center fabrics are built particularly for, with, to handle the high bandwidth and low latency. Each stage reflects growing demands for bandwidth, low latency, and flexibility. Traditional versus modern network requirements. Web applications typically need 2 to 4 backend connections, tolerate 50 to 100 milliseconds latency, and they all follow predictable traffic. AI workloads connect 128 to 256 plus nodes, needs terabits per second scale bandwidth, and require less than 10 milliseconds latency. They are bursty, unpredictable, and dominated by east-west traffic. And if you take a case study, just a simple cascading networking failure, during peak load, let us say a financial AI platform experiences IVPA timeouts. The loss is huge. The confidence will be hit low. There are so many problems that can cause if a financial AI platform experience some timeouts. So particularly this can happen. I mean, it's identified like TCP incast congestion. Basically, TCP incast congestion is where multiple servers respond to aggregator node at once. This cascades into a lot of packet drops, retransmissions, and service degradation. In data centers nowadays, we have this remote direct memory access, our converged Ethernet with flow control to prevent collapse. So this is we call ROCE or DMA over converged Ethernet. So this is one case study where we can apply RDMA, so that you- the the congestion can be avoided. So network bottlenecks, very few key bottlenecks, buffer bloat. There's a lot of buffer size increase, so that increases the latency. Packet processing limits. Traditional switches can't handle billions of packets per second. Topol, they can hand the new SX, they handle a lot of traffic, so that also has to be included. Topology constraints like oversubscription ratios, break and array workloads, bandwidth saturation, ML train can overwhelm your bits per second links in seconds. So how should a network design be? How should a fault tolerant network design be? Principles, redundant fabrics, meaning you have a path, an alternate path in case of failure, graceful degradation, and isolated failure domains. Like you isolate a failure domain so that your traffic is not impacted or only less traffic is impacted. So to have some of the strategies like ECMP equal cost multipath for path diversity, as I said, there is an alternate path for the traffic to flow and bidirectional forward detection for a subsequent failover, meaning at a very hardware level, if there is a failover of a link between two devices, that will be easily identified, that will easily propagate to the upper layers, and the alternate path is identified for the traffic, and segment routing for traffic engineering. Modern spine leaf architecture for AI workloads. The advantages are predictable latency, linear scalability, optimized for east-west traffic. Design considerations, keep over subscription below 3:1. In the sense, over subscription in the data networking refers to the bandwidth proposed to the downlink servers to bandwidth available to the uplink. So always, so which means for three downlinks, there is at least one uplink path should be available. That's what I meant by oversubscription. Use ECMP diversity. This again equal cost multipath. So the path calculation by various protocols is done and inserted into the routing tables so that traffic can be spread across multiple paths so that the bandwidth is efficiently utilized. Size buffers for microbursts, meaning there are some traffic patterns where microbursts can happen so that your buffer size can be dynamically increased to accommodate those microbursts. Consider RDMA, remote direct memory access for ultra low latency. This is network observability also play a key role because we better find problems before the users do. For example, there are telemetry, collect telemetry, like 1 second metrics that might be too fast, but that might be too frequent, but you can have some regular interval telemetry, monitor KPIs like latency distributions, buffer utilization, retransmissions, use machine learning for anomaly detection and digital twins for what if analysis. This observability always plays a key role, and you want to avoid the problems before even they do happen. So that observability really plays a key role. The hidden costs of network latency in AI and ML pipelines, even 1 milliseconds of latency can add minutes to training, 32% training efficiency loss, 2.5 times infrastructure cost multiplies, 47% is wasted GPU cycles, and 82 millisecond inference latency added to user response time. Networks delays directly translate into cost and time to market risks. Legacy switches process their 1.2 billion packets per second. AI workload needs 3 times, like 3 billion packets per second. Modern ASICs add programmable pipelines, hardware accelerated RDMA, deep buffers, congestion management, and sub-microsecond forwarding. Vendors like NVIDIA, Broadcom, and Intel, they design silicon for AI traffic patterns. Just a case study for an e-commerce platform transformation. Initially three-tier, there are all 10 gigabits per second links, 7 to 9 second page loads. After microservices, east-west traffic rose to 60% and latency spikes. After adoption, requires 100 GB per second, gigabits per second links for GPU clusters. Final spine leaves with 400 gigabits per second backbone cut incidents by 98.5% and scaled to petabytes per day. So the spine leaf architecture, it has become very powerful in the data centers where the speed is increased to multifold than the previous data centers. So the incidents are cut by 98.5% and scaled to petabytes. So yeah, key takeaways: building for the future, architect for change, design always your network should be available in, for the future changes, invest in observability to catch issues early, prioritize resilience with fault tolerant designs, optimize for latency since it directly impacts cost and time to market. Your network is no longer plumbing, it's a core platform capability. Thank you.